Let's take a practice elementary division contest number 4 ACSL exam on graph theory. Question number 1, list all edges. Circle that, it's an important keyword. Using the first letter of each person's name, so we have an L for Larry and so on. They are alphabetically arranged names, and so somewhere on scratch work, they don't always give you a lot of scratch area. You are allowed to have additional paper somewhere else. But in this video, I'm just going to squeeze my scratch work in the margin, putting a little pressure on myself. So I like to label my vertices in order alphabetically around clockwise: L, M, N, O, P. So I have 5 nodes. And the current situation is that Larry spoke with O and P. Connect those vertices with edges and check mark that you've done that. Paul spoke with L and M. Paul, see, they're not going alphabetical here. So instead of going to M next, because Paul's doing the speaking here, I'll just make a check mark there. Actually, I don't want to do that. So those 2 check marks don't actually go there. Anyway, Paul spoke to Larry and Paul spoke to Mary. So in my scratch paper, PL needs an edge and PM needs an edge. So I put 2 little check marks there to consistently follow the pattern of the check marks there. Mary's doing the speaking. Mary spoke to 3 other vertices, Paul, N, and O. So from Mary, I need to go to Paul. Well, I already have that edge. So that's just sort of a duplicate. Mary also speaks to Ned. There's no edge there currently, so I need to draw that in. And Mary here doing the speaking, talking to Olga. So there needs to be an edge between there. Be very careful with your scratch work and stay focused under time pressure. Putting a check mark there to represent that. Olga is doing speaking in this sentence to L, M, and N. Well, Olga already has L and M, but I need to represent the Olga speaking to Ned situation. Olga to Ned. So Olga has 3 edges coming out of her node, vertex. 3 check marks belong there. And lastly, Ned spoke with M and O. Well, those are already being represented, so I check mark those. Now I could, consider that finished, but you got to read the directions and know what to put in the answer box for full credit on a tricky ACSL test. List all of the edges. So the edges are represented by these short line segments. Technically speaking, you can list them in any order, and as long as you're using the first letter of each person's name, and be sure not to include any duplicates. So there was a risk that if you didn't draw your picture here to realize that there were a lot of duplicates worded in this paragraph, you might list duplicates accidentally if you just directly went from the paragraph into an answer without making the drawing. Okay, so I'm going to systematically start with L in the alphabet here. L, there's no node edge that goes from L to M, but there is N and O and P. So LN, LO, and LP. M has alphabetically N, O, and P. So M has these edges that I need to put on my answer key. And emanating out of M, N goes to M, L, and O. Being careful here. I missed one there. I missed the NL alphabetically. And the node P only has L and M. So there I have complete listing, but now with the eraser on my pencil, I need to make sure to erase the duplicates. Well, LN is the same as NL. LO isn't being represented anywhere else. I don't know how I missed that duplicate, but it's not. The LP was here. MN is already represented there. MO, I missed that one also. The second time around is OM. MP is double counted there. And NO, I don't know. I did not double duplicate that. Using my eraser, even though probably you would get credit for having the line through the ones that you struck out, especially if you're under time pressure, doing this one maybe last after doing some of the other questions. So at this point, I'm going to change my color of my marker. You wouldn't be, well, unless you have a pen. Yeah, that would be a tip. On test day, have a pencil and a pen and go back and now double check to make sure that you represented everything exactly once. Check mark, check mark, check mark, check mark. That's 2, 4, total 4, 5, 6, 7 so far, 8, 9, 10, and 11, 12. But because of their perfect wording, being they don't try to trick you. 12 divided by 2, since Olga does the speaking here, but somewhere else, for example, Larry speaks to Olga, so that Olga Larry connection is double counted. So because I counted 12 individual check marks there in my blue ink as well as the red ink, if you want to double check, I should have 6 here. I have like impossible unless they worded it in a way that it's not symmetrical. So I go through this and just make sure NO does have. So anyway, I could count the edges here. 1, 2, 3, 4, 5, 6. One of these is extra. So to get full credit here, I'm with my blue ink as opposed to my pencil. I'm going to write over these to make sure I know which one I missed. MN, MO, MP, and NO. So I did count the right number of edges there. I'm going to go through my sentence, and maybe I should have a total of 14. Maybe I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I am counting 12, and maybe this question wasn't worded symmetrically like I was alluding to. So I made this problem up, and maybe I missed that double coverage. I'll let the video audience alert me, perhaps on my YouTube channel, with a comment as to what I've missed. But I, on this answer key, am sticking with this as my final answer. And Larry does not speak to N. That's what's missing. LN should have never had a node. This was bad. LN is not mentioned here, and neither is NL mentioned in the Ned sentence. So that's just a mess up right from the very beginning. That 12 is correct. This 6 is correct. So I'm finished with exercise 1. Exercise number 2. Key words here to emphasize under test pressure. We need to identify edges again in this question to make this a complete graph. Now, if you don't know what a complete graph is, at this point, you'll need to study it in any way, shape, or form you can, from notes, looking up on the internet, asking a tutor, etc. But for this to be complete, there needs to be edges between all pairs of nodes. So I need an edge there. That's one answer. And I like to go alphabetical order, so EF rather than FE. And this is just by what we call inspection. I should find a pattern here. I'm going to start with A. Pretend that I didn't do that one yet. It was just so obviously missing there. A, because there are 5 other nodes from A, there should be 4 lines or edges emanating out of A. Well, I only see 4, so A is missing an edge with somebody. Yep, right there it is with E. B only has 5. Well, that's perfect. So B is sort of complete as a node. C only has 4. Which one's missing? Oh, they made this a little tricky. It was hard to see that because these aren't spaced nicely, equidistantly. D only has 4 edges coming out. So D is missing this 5th edge to F. E, we already caught the EF. 1, 2, 3, 4, 5. It is now complete. And finally, F is complete with 5 nodes. So these blue lines 1, 2, 3, 4 are the 4 answers. Technically, you could have wrote FE to get full credit there. You don't have to go alphabetic. Oh, yeah, no. In this question, they're saying list them in alphabetical order, A, B, not B, A. So that is the only correct answer as far as the EF goes. A needs an AE, and I don't like putting that out of alphabetical order. So I'm going to redo this AE. That counts for that one. And then coming around here, I have a blue one emanating out of the C. So that needs to be written as CE. D has has just F coming out, so DF. And finally, E has 2 nodes, but the one was already listed over here as CE, and we certainly don't want to list duplicates. So E needs the EF representation of an edge. So making sure we're delivering to the exam folks what they asked for, identify the set of edges. Yes, this is a set of edges. Maybe you would put a set of what we call sometimes curly braces and put commas here as this what we call a set. But in the elementary division, the original answer there was also acceptable. In number 3, now this is not a very technical question, except for the fact that they mentioned Hamiltonian circuits, which you really don't need to know to do this problem. Starting at A, we need to go all around the nodes and vertices in the neighborhood, if you will, and return back to A, making sure that we visited each other house in the neighborhood once and exactly once, and we end back at A. That's what they're trying to get across in this question. Well, I just defined what it means to be a circuit, also known as a cycle, and a Hamiltonian. In the case of a Hamiltonian, we just have to make sure that we hit all the edges, and that is part of the definition of Hamiltonian, that we travel all of these paths, and we're trying to figure out how many routes we can take to do that. Well, let's see here. In this case, A, find a pattern that works. So I'm going to start with, this is a tricky problem. This one's going to soak up a lot of time. A can't go to B. So I'll use as sort of my route AC as a starting point. So if I visit and deliver an invitation to the person that lives at C, I could then on my bicycle ride to either E or D. I can't go to B. So I'm going to branch out in my planning for this project, this problem, and pretend that I went to D. But I'm also going to come back and use sort of this binary branch and pretend that I went to E. So if I went from A to C to D, and I still need to go to these 2 nodes, well, I can see visually by inspection that if I go to B, I can't get back to A. So that rules out the path to B. ACD to E does get me back to A. So that is a successful branch, Hamiltonian circuit. And I will list that as 1. There was no way. So I sort of exhausted ACD as a starting path. ACE, let's consider anything that comes out of ACE. So if I go to ACE, I still have to hit either D or B or either one and get back to A. Well, I can't go to B and get back to A, so I can see that visually. So again, ACED does take me back to A. Bingo. ACE, and then D and back to A. So there was another part of my answer. So I just exhausted all the starting trips with AC. It looks like A can also start out with D. So changing color here, that could be the start of another nice little pattern systematic way to, by inspection, solve this problem. So going to A to D, I could always go to B. So B is a possible branch next. AD could also branch to C. And oh my, AD also possibly branches to E. Focusing on the B, AC, or I'm sorry, AD, B. So I still have to hit C and E. There's no way to get directly to C, but I can go to E and then CA. So that is a solution. Also, A, D, and now considering C as a possibility, ADC. ADC, again, from B, I can't get back to A, so A, C, D, E, but then I would have to go to B and I can't get back. A, C, D, B, that's what I meant to say there, which was the next step. Again, A, C, D, B, and then I can go to E and get back to, oh, but that was out of play because the D can't be visited twice. So that there was no other path that came out of ADC. Okay, thirdly here, ADE, A. I still have to hit these two. Mapping it out, if I go to C, I can't go to B and get back to A. If I go to B, I can't get directly to C and go back to A. So there's nothing that comes out of that sort of route. Oh my. So I've now satisfied all starting possibilities from A to D. And the last one I have to consider as the first pair is AE. Coming out of AE, changing my color once again. Coming out of, I meant to change the color. Coming out of AE, I could branch to B. I could branch to C, and I could branch to D because, well, E is a popular vertex. Going to B, I still need to hit these two. I could go to DCA. So DCA is a possibility there. And again, AE, now possible C. And it looks like I cannot go to D, B, and get back to A. And I can't go to B directly from C, so that's sort of out and unproductive. And lastly, in this case, AE, D, AE, D, I still have to visit these two nodes right here. AED, oh, if I try to go to C and the B, I can't go home to A again. And if I go to B, I can't get to C to go home again. So that's a dead end for this particular problem. Okay, well, A has no other edges going anywhere else other than C, D, and E. So I've exhausted my systematic sort of examination of that graph. Be careful that you don't list duplicates, and we're not really finished yet. We have to record, first of all, we have to record our answer. And the question is how many? So we need a number here. We don't want to list all these. Are there duplicates here? Oh, first of all, the definition here of a such circuit is that in this case, each one of these can be listed the other way around and it's considered a different circuit. So wait, did I miss something? AC, D, E, A. I missed B here. So actually, yeah, because I was going to say this, there was too many answers here. This was not a complete path. Sorry about 5 minutes ago. I was rambling about nothing. Those are not complete. So we end up with this path and this path that are Hamiltonian circuits. So I do list those two. Oh, no, I'm sorry. We don't list anything. Those are two paths, but consider A, D, B, E, C, A in that forward direction. A, D, B, E, C, A. That is a way to ride your bicycle, but you could also take the reverse order and start with A here and go to C and go to E and go to B and go to D and go back to A. That is considered a different circuit. You're just riding your bicycle the other direction. Same houses in the same reverse order. So this entry right here counts as 2, and this entry counts as 2. So the answer to this exercise is a total of 4. You should always get an even number here. And I do want to go back to exercise 2 and stress that there's a formula. If you, I'm so sorry. There is a formula, and I don't know what I just did there. Oh my. There is a formula that we could use for making sure that we got the right answer here. That formula is that the number of edges overall in a complete graph is equal to the number of vertices plus the number of what are called diagonals. In this exercise here, we obviously had 6 vertices. The diagonals are these inner edges, not the ones around the perimeter here. So we ended up having 6 diagonals if you count the, like AC as a diagonal, AD, and E. So there was 3 there, diagonals from A. If you add them up, you get 6 for this particular graph. And the number of edges overall, well, there were 6 already drawn here in this grayish color, plus the 4 that we added does, I'm sorry, there were 8 if you count the number of edges, including the ones around the perimeter there. So it ends up being a total of 12 edges in this with the blue ones that we added. So it is complete here in that exercise. I have notes or previous worksheets that you can look over to see that formula as a check if you have time to check your work on this test. Exercise 4. Everything in the elementary division is undirected. There are no arrows on these graphs. So don't worry, it's just extraneous information given to you in this particular exercise. How many cycles? Well, in this case, a cycle that only has to be 3 or more vertices. It does not have to completely map the neighborhood, traveling over each edge exactly once like that problem. In this case, it's just getting back to the original vertex that you started with. Well, and anything with like at least 3. So let's find a pattern. You cannot start with A as part, if you do start with A and you go to E and you come anywhere else and go back to A, you've repeated E again. So A is out as the starting vertex of any circuit, a cycle. In fact, it's out. It can't be part of any cycle because E will always be double counted. So considering this graph right here as really the working graph for this exercise, let's just start with B because alphabetically. So we need at least 3 vertices. Well, yep, B, C, D and back to B is a cycle. B, D, E and back to B is a cycle. So that's pretty much everything. Then also the whole way around this perimeter of 4, B, C, D, E is a cycle. So there are all the cycles that use B as a starting point. And I was just, sometimes we write the node again just to show that we got back there. So that's 6 of one, half dozen the other if you put the B there in your scratch work especially. Okay, starting with C. Well, C and D, B back to C is the same cycle as this one. It's the same sort of like trip around the bases, if you will, in a sport like baseball or softball. So that one has already been counted. However, you can go both ways. So in other words, we've already counted this purple shaded in circuit. We've already counted this one right here. And we've already counted the one that's the superset of both of those triangular regions. So we've already counted all 3 geometric shapes there. And but each one is considered a different cycle. So BCDB, along with going in the opposite order, B, D, C, B, B, D, C, B, count as 2 towards our answer here. And this also has a reverse order, B, E, D, B, And this one right here has a reverse order, B, E, D, and so on. So you have a total of 6, and your answer here to this exercise is 6. Again, we did that just by inspection. They're right now without a computer program and some fancy formulas. There's no easier way to do this in the elementary division contest than to come up with patterns and use computational logic and systematic thinking and just working fast under pressure without making mistakes. Number 5, identify the starting and ending vertices that must be used to traverse the following graph. To traverse just means, well, it's called an Euler path. It's in the vocab list that I have produced somewhere, but you must hit each of these. You must traverse the whole path. You must travel over the whole thing. So the formula that's in my notes somewhere or that you'll find on the internet is some graphs are not traversable. So the answer may be none, as they're suggesting here in the exercise. The key at this point in your abilities and know-how is to go to the edges, go to the vertices, I meant to say, and count how many nodes come out of each edge. So A has 2 edges coming out of it as a vertex. B has 2 edges coming out. G has 2, as you see here. For some reason, I have trouble writing with my pen. So we have 2 there, and now, oh, bingo, we have 3 there. I wanted that. We have 2 there, and we have 1 coming out there. Anytime that you have odd numbers of edges coming out of a vertex, those are candidates to be the starting and ending points for a graph that can be fully traversed. So the answer to this exercise is C and E. No matter how you list it, C and E are the starting and ending vertices that would have to be used if, and I'm just going to wing it here to see if I can, just for fun. You would not have to do this on a time test. But starting at C there, starting at C, I cannot go to, oh, C is going to have to be the, starting at C, I can only go to E, so I will. I paired them up, you see. And now from E, I can go around this graph and get back. So you see, well, from E, it just looks like I should go to F there. It just kind of looks close and everything. From F, I only have a choice to go to D. From D, I only have a choice. I came in from F. I have to go to G. And from G, I have to now go to B. And at B, I have to go to A just because of the evenness of all this. And A takes me back to E. Now notice I have not traveled that highway, that edge yet. That was still available as a road. And now that I'm at E, I can get back to C. Again, you can travel this is not Hamiltonian. You can travel the edges more than once, but you have to get back to where you went. So I believe I did that correctly there, showing that that was traversable. If not, catch up with me and I will clarify it. But C and E are definitely the edges that have to be used let me just think this out one more time. Oh, you know what? I should have started with E. Yeah, I'm sorry. Scratch all that. This is all like after the exam's over anyway. The answer is still C to E because of that formula, but starting with E because it had 3 edges coming out of it rather than that 1. I don't want to go to C. I have to save that for the end. So in this type of path, Euler path, we can visit edges more than once. We just are not supposed to travel over the, we can visit vertices more than once. We just can't use edges more than once. So E to F is my only way, is one way to start this. To D, to G, to B, to A, and then to E again, because we had not traveled that path yet, and then finally to C to bring us home. There is proof that it's traversable. All we need is just one example to show that that's traversable, and the answer is not none. Anyway, the answer was C to E because of the formula. There you have it. Good luck on the exam.